right, so what happens if things are not moving in equilibrium? All right, what happens if there is an acceleration somewhere? So we're going to discuss, so when we look at Newton's second law, we have that the sum of the forces looks like the mass times acceleration. And there ought to be something for the for this that looks like the sum of the torque is going to look like something, which I'll call I at the moment, times the angular acceleration. All right, and we can kind of arrange this thing. The force here is, hand wavy. It is sum of the torque over the radius. Not exactly right, because we ain't defined division by vectors, but just bear with me a minute. And then we have the mass times r alpha for getting the angular acceleration. So this thing we can kind of rearrange is sum of the torque looks like the mass times the radius squared times the angular acceleration. And this thing in parentheses is effectively looks like the mass for a rotating object. Right? We have our rotating object here. And the reason why there's this great big hunk of brass there is because if all the mass is on the axis of rotation, it doesn't rotate worth anything. It just kind of falls over. You need to have some mass away from the axis of rotation to have the inertial effect that you expect, that it'll stay rotating or it'll accelerate. Right? So the mass that's away from the axis of rotation is the bit that feels the torque and gains an acceleration. The stuff at the axis doesn't rotate. It effectively stays put. So this is our rotational mass. Which is our moment of inertia. So the idea is if we have a point mass, so we have something just going around, like here's a rubber band, and we're just going to make this rubber band go, and our funny spinning mass, I'm just going to make it go around my finger. All the mass is at one point. It's all at the end of the rubber band. So in that case, our moment of inertia, I, is mr squared. For any other distribution of mass, well, there is a generic way of dealing with it. We can say, effectively, we're going to take an integral over where the mass is, and it's going to be an integral of r squared. This is no bueno. Like, I don't expect you to do this. I don't expect you to even know what I'm talking about. What this is effectively the density times some volume. And so this will be dx, dy, dz. And so this is a three-way integral. I don't expect you to do that at all. So that's how it can be explained in the textbook. Instead, there's something like a set of charts that you can see in your textbook. And there will be a ring, and I is mr squared. A cylinder, I is 1/2 mr squared. And there'll be a bunch of these things. I'm going to pause the video so I can show you that chart in a second. But the gist of it is this constant, for any other thing, I is some constant times mr squared. And this constant comes from this integral. You're always going to get this r squared times the mass, but there's always going to be some other constant that tells you basically the shape of the material. So let me pause the video and I'll come back with those diagrams you want. So this is what your textbook uses. Focus. There we go. Your textbook has this thing here. And, it's a chart of the different possibilities. You can have a thin shell or a ring, and this has all the mass out at the radius. And so the moment of inertia is mass times radius squared. For a solid cylinder, a lot of the mass is in at the center of the cylinder, and the average effect is as if all the mass were halfway out of the radius. Right? Here we have a bar that's rotating about the center. Here we have a bar rotating about one end. We have some spheres. We have a rectangular plate. But what's happening here is we're adding up all of the different point masses. And that looks like doing this ugly focus. That looks like doing this ugly integral. Let's zoom in. All right, and of course, it's going to be some sort of doing a volume integral. And we haven't defined what a volume integral is in this class. So try not to worry too much. You're going to be looking these things up. And of course, there'll be some version of this will be provided to you on assessments that you have. I may have to send that out to you. But the gist of it is, whenever we're trying to find moments of inertia of an object, we're going to add up a bunch of moments of inertia for something else. So let's zoom out here. Let's say I have a wagon wheel. Okay. And we're going to make this special. It's going to be 4 horizontal bars and then a rim and then an outer rim like that. That's going to be our wagon wheel. So we can break this into components. This is a thin shell. And so that's going to be our thin cylinder. And so I here is going to be the mass there times the radius squared. The mass of the cylinder times the radius squared. And then there are these spokes. And what we can do is say that there are 4 of them with radius r. So there's 4 of, and then we look up what this is. And for something rotating about one end, it is 1/3 the mass of a spoke times the radius squared. And so we can do other, the idea is that if we have a complex object, we can break it down into simpler objects and find the appropriate moments of inertia for those simple objects and then add them back up. So there's one more thing that's talked about in your textbook, and that's, we're assuming that this object rotates about this point, but what if it rotated about a point over here? Which I'll call the distance to the center of mass. So you can imagine, we spin this top like this, and that makes sense. That is the object spinning right there. But what if instead we had it orbiting that point? All right, so we have something that looks like this, and it's moving around like that. What does that look like? Well, what we can do is take, this is what's called the parallel axis theorem, is that any moment of inertia can be shifted. So you can add on. So the idea is that all of these things that we're talking about in the textbook, all of these in the charts, which are not where I left them here, all of these things, you'll notice that there's I center of mass, ICM. They're assuming that everything's rotating roughly about some center of mass. This one's not, but this one you can derive from this one, it is. So most of these, everything's rotating about a center of mass, and you can simplify things out by effectively having one set of things for the object and then saying how it's rotating somewhere else. And so I do have something I want to show you here, and it's going to take me a minute to set up. Give me a moment. I'm going to pause the video again. Hello, students. I don't think this is interesting enough, but I want to show it to you directly. This is just a regular old box of paper. So there is a way that this spins very nicely like this, like a pizza. If I can spin it correctly. All right, you can see the side that's up. You can see the other side, the stuff with more stuff on it. Spinning it like that does okay. Spinning it like this is fairly straightforward. Or is it? No, it's not. Spinning it like this. All right, so notice where the lid is in the video. It's here. I want to spin it like this, and the lid is still there. And I'm going to spin it like this, and the lid's still on top. Lid's still on top. So now I want to spin it like this. Not this way, not like a pizza, and not like this. I'm going to spin it like this. And when I do that, I have some problems, right? So note the lid is going to be down here. So when I spin it, and the lid moved. Let's reset that. The lid's going to be toward me. I'm going to spin it, and the lid's away from me. How did that happen? What you notice is as you saw it spinning, it tumbled. So this thing has moments of inertia. You can look it up in your textbook. It's 1/12 the mass times the sum of the sides squared. Right? Because this thing has a weird distribution. And so what happens is there's 3 different axes it can spin on, the 3 that I showed you. You can spin on other ones. I can try to spin it around a corner. I can try to spin it like this. But ultimately, there's what's called 3 principal axes. It can spin that way, it can spin that way, and it can spin that way. Those are axes. 2 of those are real easy. One of them has the biggest moment of inertia. That's this. This has the pizza spin, puts all the mass as far away as possible. And it's a nice stable way to spin it. If I make one turn, everything stays upright. It doesn't try to spin around any other axis. One of them maximizes the moment of inertia. One of them minimizes it. If I spin it like this, and don't drop it, if I spin it like this, it puts the mass as close to the axis as possible. But this one, the intermediate one, kind of is in between, and it's unstable. That causes, if I don't spin it perfectly, see, I can do it kind of slowly, but if I do it fast, it tumbles. And that tumbling is because it tries to rotate around one of the more stable axes. This is what's called the intermediate axis theorem. This is also what's called the tennis racket theorem. If you all have a tennis racket, try this. Spin it around the handle, Then spin it like pizza tossing, and then try to spin it the other way. And what you'll notice that it's the tennis racket flips over when you spin it the other way. I'll have to get a tennis racket and actually show you that. We're going to pause the video and go back to something else.